Hey everyone, welcome to the start of the lecture videos for Chapter 3. So in Chapter 3 we're talking a lot about second order equations. So Chapter 2 is about first order, Chapter 3 is about second order equations. And in particular we're going to spend a lot of our time focused on second order linear equations because we can solve them. They're easier to solve and we can actually, work with them and see how they work. Along with the fact that second order linear equations provide us a lot of decent mathematical models for certain systems such as masses on springs and LRC circuits in electromagnetics. So in this first video, we're going to talk about second order equations in general, what second order linear equations look like, and how we can start talking about them from here on out. So let's go ahead and jump on into that. So section 3.1 starts off getting us through the basic definitions for second order linear equations, what it means for an equation to be linear, and then some other terms along those lines. So if we're basing off what we had before for first order equations, what should our general second order equation look like? So a general second order equation is of the form d squared y dt squared equals some function of t, y, and y prime. Right, so our general first order equation was dy dt equals f of yt. In this case, second order equation means our highest derivative should be second order, and we're going to again assume we can isolate that second order derivative. And so the general second order equation is d squared y dt squared equals f, some random function of t, y, and y prime. Now, how do we know if such an equation is linear? Well, the idea is the same as it was before, right? Before we had that it had to be sort of a linear function in some sense of the y function on the right-hand side of the equation. In this case, we need to be linear in both y and y prime. Which means I can't have y squared, I can't have y times y prime, I can't have the sign of y prime showing up in my equation. If it's going to be linear, it just has to be the y's by themselves, not really interacting with each other. And if not, the ODE is called nonlinear. Now, just like before for first order equations, if a second order equation is linear, it has a very specific form, right? It means that I have to have, the only things I can have on the right-hand side are functions of t, or y times a function of t, y prime times a function of t. So in particular, we have a general form for these equations. The general second order linear equation has the form d squared y dt squared equals some function g of t minus some p of t dy dt minus some q of t times y. Or I can reorder this to say that d squared y dt squared plus p of t dy dt plus q of t y equals g of t. So this should look vaguely familiar from how we set up our first order linear equations, right? We had dy dt plus p of t y equals g of t. Now here we just have two functions of t because we have a dy dt and a y that both can get functions attached to them. Now we have characterizations of these equations based on this function g of t. So we say that an equation is homogeneous if this function g of t is 0, as in if we just have a 0 right-hand side, and non-homogeneous otherwise. Now, to be honest, I'm not sure if it's supposed to be homogeneous or not homogeneous. I usually go with homogeneous, but any of those, either way you say it, it's going to be fine. So it's homogeneous if the right-hand side is just 0, and it's non-homogeneous otherwise. Now we're going to be talking about these equations in two different types, in two different sections. So we'll be talking about solving the homogeneous equation here and in the next couple sections. And we'll move on to solving the non-homogeneous case. So we'll start by solving the homogeneous case, which it'll turn out is an important part of solving non-homogeneous problems. And then move on to actually solving the non-homogeneous part once we get there. So the first type of equation we're going to look at are the simplest of all of them. We're going to be looking at homogeneous and constant coefficient equations. So what that means is that my p of t and my q of t are just constants. They're just numbers. They're not functions of t. So they're guaranteed to be continuous and smooth and all that stuff, but they're just constants. It turns out that's a really easy equation to solve. So we're going to start there, figure out how to solve those, and then work out to more difficult equations as we move forward. So in the book, we're not really going to be doing too much of non-constant coefficients. We'll talk about it in the theoretical section, but overall, all the problems we solve are all going to be constant coefficient equations because those are easy to solve and we can actually talk about models using those equations. So we're going to start with constant coefficient equations. Start with homogeneous and constant coefficient. So what that means is that our equation looks like this. Our equation is going to be some constant a, d squared y dt squared, plus some constant b, dy dt, plus some constant c times y equals 0. And for section 3, the rest of this section, and then 3.3 and 3.4, we're going to be dealing with this equation exclusively and figuring out, okay, how can we find a solution to this equation, whatever a, b, and c might be. So our next steps are to work on that, and then going on that, the equations will get harder and harder, but we're really just going to keep coming back to how we solve this equation right here. All right, so there's the first video for this section. The main things here were the definitions of homogeneous, inhomogeneous, non-homogeneous, I guess is the term they use here, and then linear, nonlinear, and constant coefficient equations. So now I've got a couple examples for you to look at, which is just verifying solutions. So this is stuff we did way back when, but you'll see these equations are second order linear. And then the next couple of days, you'll see how I got to those solutions for these equations that I'm going to present to you now. All right, so I'll throw those problems up for you right now. All right, so here are two for you to look at. Just quick verifications that these guys solve their problems, their corresponding equations. And then the next couple of videos, the next couple of sections, we'll see how we get these solutions and how we derive them. All right, thanks for watching, and I will see you in the next one.